Now, what is a vector space? We define a vector space over a field. So the scalars that we saw that we were scaling our vectors with come from the field that we defined previously. So a vector space over a field is first a non-empty set, right? So we need your set V to be non-empty, but with two operations. We said we can what? Add or scale vectors. Okay. So vectors can be added or they can be what? Scaled, such that some axioms hold. Now, if you add two vectors, you want to stay in that set V. So if you pick three elements U, V, W in V, and you add them, you want to stay in V. And if that property is satisfied, that's what we call the closure property. Similarly, if you have three vectors U, V, W, there are two different ways of adding them. You first add two and add the third, or you add the last two and add the first. You want them to give you the same answer. And this property is what we call the associative property. Thirdly, you want a do-nothing vector, right? So it's just stay where you are, you don't move in any direction. So do-nothing vector is what we call the identity. So when you add it to any vector, you remain the same. And we saw a vector in its reverse, right? So if a vector is going in one direction, the reverse goes in the opposite direction. So, and we said that the direction we will attribute with the negative. So if you have a vector, its reverse direction is negative, and when you add a vector to its reverse, so you move forward, wherever you end, you return, it gives you back. So we can think of it this way. So if you have your vector U this way, and so you move from your starting point, that will be U. Now, if you want to find U plus minus U, we said that minus U is same vector but in the reverse direction, right? So U plus minus U means you go U this direction, then wherever this ends, you start with your minus U. So we move our minus U here again. So you start from here, you end getting up, you apply your minus U. So you see, we started here and we've ended here. That's how come when you add a vector to this additive inverse, it means you did nothing. So this is what we call the inverse, right? We call this the inverse under addition. And similarly, we want the addition to be commutative. So we want the order in which you add the vectors not to matter. So whether you do U plus V or V plus U, you want it to be the same. So this we call the commutative property. Now the set V under all these operations, we say that what V under addition is what is an abelian group or a commutative group. But those are not all the axioms. We want to scale vectors, right? You want to scale vectors. So if you have lambda in your field and you multiply it by your vector U, so you want what? Scalar multiplication. And also, we've seen that there are two operations now. You want the operation of addition and the operation of scalar multiplication to interact very nicely. So if you add before you scale, you want to be the same as what? You scaling before adding. And we call this what? The distributive property. So you want the distributive property to hold. And similarly, if you have two scalars which you add before multiplying by a vector, you want it to be the same as you were scaling before adding. So it's also the distributive property. Then if you have two scalars, you can choose to multiply the scalars first before multiplying by a vector. It should be the same as you multiplying the scalar, one scalar by the vector, second by it. And we call this the homogeneity. And finally, we saw that in a field, we always have this element 1, which we call the multiplicative or identity. You want that when you multiply this multiplicative identity by U in a vector, it should give you the same. So let's say what the units. Okay. So these are the 10 axioms that gives you the definition of a vector space. Now, when we think of